Let us talk about this problem. We are given a number n. Our task is to print prime factors of this given number. What are prime factors? Prime factors are those divisors of the given number which are prime. If you see n equal to 12, it has multiple divisors, 2, 4, 6, 3, 12 itself. But out of all these divisors, which divisors are prime? 2 is a prime number, 3 is a prime number. And 2 divides 12 2 times. So that is why we write 2 2 times. Just to recall what prime numbers are, here I have written first few prime numbers, 2, 3, 5, 7, 11, 13. These are first few prime numbers. Let's take another example, n equal to 13. So its only divisors are 1 and 13, but 1 is not a prime number. So we are going to write only 13. Let us see this example. It has multiple divisors, but the prime divisors are 3, 3, 5, 7. 9 is also a divisor of it, but we are not writing 9. We are writing only the divisors which are prime. And if you notice one thing about this output that we are producing, if you multiply all the numbers in output, you get the original number, right? Because if you're simply writing all the prime factors only, right, you won't have any multiples of these prime factors. And these prime factors, when they're multiplied, they will give you the original number. Now please pause this video and try to write down a function that takes n as an argument and prints its prime factors. Let us first talk about naive solution. The idea is to run a loop starting from the first prime number, which is 2, and traverse through all the numbers from 2 to n minus 1 and check if this number is prime, because we want to print only prime divisibles. If I is prime, then we check if n is divisible by I, right? We have initialized a variable x equal to I, and then we are checking if x divides I. If that's the case, we print I. Now why are we using another variable x? Because multiple powers of I can also divide n. For example, n is 12 here, right? 2 divides n and 4 also divides n. So for those cases, we are using another variable x. We are initializing it with I, and then we are doing x equal to x into I. We are taking next and next power of I. And if next power also divides, we print I one more time. If next to next power also divides, we print I one more time. That's the idea we have in this implementation. So for n equal to 12, we'll begin the loop for I equal to 2. We'll see that 2 is prime, right? And what we'll do, we'll initialize x equal to 2, and n is divisible by 2. So we'll print 2. And then we will make x equal to 4. Then we will check n is divisible by 4, yes. So we will print 2 one more time, and we will make x equal to 8. Now n is not divisible by x, so we will stop here. So we will print 2 2 times. Then we will come to 3, and 3 is also a prime number, so we will come inside and we will print 3, and then we will make x equal to 9, and 9 does not divide 12, so we will stop here. And then for I equal to 4, we will not go inside this because 4 is not prime. For I equal to 5, we will go inside this, but we will not go inside while loop. So we will never go inside this part, and we will never print the numbers if numbers are greater than 4. We are simply going to get 2, 2, 3 as output of this program. Let us now analyze time complexity of this solution. We have a loop which is running theta n time, and then we are calling its prime function. This function is also upper bounded by n, right? So it's going to take big O of n time. And then we are running one more loop inside it. And inside this loop, we are starting with a number x equal to I, and then we are checking if n is divisible by x, and then we are incrementing x with x into I. So when you have such a loop, this loop can take at most big O of log n iterations, right? This x can reach up to n, and it is multiplying itself with I to reach n. So in those cases, it's going to take at most log n steps. So we have log n steps here, and then we have n square steps here. So an upper bound on time complexity is going to be big O of n square log n. Now please pause this video and think of an optimized solution to solve this problem. Let us now talk about ideas for the efficient solution. The first idea is divisors of a number appear in the form of pairs, and this idea has been discussed in prime number checking video also. So this is the same idea that we discussed there. For example, if there is a number 30, and if I talk about all of its divisors, I can notice that 1 and 30 are two divisors. They form a pair. If you divide 30 by 1, you get 30, and if you divide 30 by 30, you get 1. Similarly, we have other pairs, 215, 310, 5, 6. So if I consider a pair xy, then I can write xy is equal to n. That's how these pairs are. And if I consider the smaller of these two divisors, smaller or smaller than equal to of these two divisors, then I can say x into x is smaller than equal to n using this and this. And from this I can conclude x is smaller than or equal to square root of n. From this I can conclude that if I traverse from 2 to square root of n, 2 to square root of n, I will get a prime divisor if there is a prime divisor, right? Prime divisor other than 1 and the number itself, then I'll get that prime divisor, right? If I simply go from 2 to square root of n. This is one conclusion. And this is the same conclusion that we use in prime number checking video as well. Let's now talk about the other important fact, and this is the main basis behind the algorithm that we are going to talk about. So we can write the given number as multiplications of powers of prime factors. For example, 12 can be written as 2 raised to the power 2 multiplied by 3, and its prime factors are 2 and 3. 450 can be written as 2 raised to the power 1 multiplied by 3 raised to the power 2 multiplied by 5 raised to the power 2. These three are prime factors. 3 appears 2 times, 5 also appears 2 times. We can write any number as multiplication of powers of prime factors. And if the number is prime, we can write the number as itself, right? 13 raised to the power 1. So the main idea that we are going to use in this algorithm is find the first prime factor, and you are sure that the first prime factor, if there is a prime factor other than the number itself, then the first prime factor would be in range from 2 raised to 2 to square root of n. So if there is a prime factor, you will find in this range. And once you find the prime factor, you are going to divide the number by this prime factor repeatedly while the number is divisible. So for example, if you have the number as 12, you will find the first prime factor as 2, right? And you will notice that 12 is divisible by 2 times. So you are going to divide 12 2 times and you are going to print 2 times. And after that, you are going to reduce your number to 3. And if you see this example, you will find the first prime factor as 2. You will divide 450 by 2, you will get 225. Then you will divide it by 3 2 times because it's divisible by 3 2 times. Then you will get 5 square. Then you will divide this number 5 square, which is 25, by 5. And you will notice that you can divide it by 2 times, right? Because it's divisible by 5 raised to the power 2. So that's how you are going to follow. You are going to find the first prime factor, divide the number completely by this prime factor, then find the next prime factor, divide the number completely by this prime factor, then find the next prime factor, divide it completely by prime factor. And that way you can find all the prime factors. Now please pause this video and try to write down implementation of this efficient idea. Let us now see implementation of the efficient idea. So what we have done here is, we first check if n is smaller than or equal to 1, then we return. Please note that there are no prime factors for 1, because for prime factors the conditions are the number should divide it and it should be a prime number. So 1 itself is not a prime, and 1 is the only number that divides 1. So anything which is 1 or smaller than or equal to 1, we will simply ignore it. For other numbers, we will run a loop from I equal to 2 and we will run the loop till square root of n. So instead of computing a square root of n, I have written I into I smaller than or equal to n, and then I plus plus. And if current number divides I, then we are going to print I. See, this print syntax can be replaced with cout in C++ and system.out.print in Java. So we print I and then we do n equal to n by I. We keep doing it while n is divisible by I, right? And once we come out of this loop, and if now our number is greater than 1, then we'll print the number. I'll talk about this corner case with another example. Let's understand the execution of this code with this example 450. We have discussed earlier that 450 is 2 raised to the power 1 into 3 raised to the power 2 into 5 raised to the power 2. So what we do in this execution or this logic is, we first take out 2. And we know that if 250 is not a prime number, then its first prime factor is going to be present from 2 to square root of n. So we find the first prime factor as 2. We divide n by 2. So our remaining number is now this, 3 into 2, 3 raised to the power 2 multiplied by 5 raised to the power 2. Now for this number, the same logic applies. its first prime factor should be from the current value of I to square root of n. See, why are we taking current value of I? Because the loop keeps running for increased values of I, and we have already checked for numbers smaller than the current I, right? So it should not be divisible by them, because if it was divisible by smaller numbers, they must have divided already. So now we begin with 3, and we find that 3 is dividing this number 450. So we take out all the powers of 3 from this, and our remaining number gets the last prime factor, 5 square, right? So we take out all the powers of 3 and we print 3 two times. So inside this loop, we are first going to print 3, then we are going to divide the number by 3, we get 75. Then we are again going to print 3 and divide it by 3 again, we get 25. Now we have the number n as 25, and we have come out of this loop, so I is going to increment next time and I is going to become 4. Now we check if 4 into 4 is more than equal to 25. It is more than equal to 25. So we are going to get inside the loop for 4. But 4 is not dividing 25, right? So we do not go inside the inner while loop. Next time we run for 5. When we run for 5, we notice that 5 is dividing 25. So we are going to print 5 two times. First time we print 5, then divide the number 25 by 5, we get 5. Then we print 5 and we get 1. And when n becomes 1, this condition becomes false, because now I is 6 and 6 into 6 is smaller than equal to 1, not true. So we come out of this loop, we check if n is greater than 1, no, so we don't print anything. And we have printed the required prime factors. We have printed 2, 3 two times and 5 two times. Let us now do a dry run of one more example. Let's say n is 84. So we'll begin with I equal to 2, and 2 divides 84. So we'll print 2 and we'll reduce it to 42. Then we'll again print 2 and we'll reduce it to 21. Then we'll go for I equal to 3. 3 also divides. So we'll print 3 and we'll have n equal to 7. Now after n becomes 7, your I increments and becomes 4. And 4 into 4 is not smaller than equal to 7. So you're going to come out of this loop. And when you come here, you notice that n is greater than 1, because n is 7 now. So you are going to print 7. So in this case, we are coming out and printing 7 explicitly. See, if your number is like this, what this logic is doing, it's one by one taking out prime factors and their powers and printing those prime factors those many times. So we take out 2, then we take out 3. And when your last prime factor, the largest prime factor, has only power 1, you would fall into this case. Because in those cases, you will not find a prime factor, right? If the last prime factor, the largest prime factor has only power 1, then the last number, remaining number is your prime number, right? So for a prime number, you will not find a prime factor, right? So you will have to print the last prime factor explicitly. That's why we have added this if condition. We can further optimize this code using the same idea as we discussed in the prime number video. If I explicitly handle prime divisors 2 and 3, I can avoid checking for many other numbers, and this way I can save many iterations of this loop. Let's say the current value of n is n, and we are running this loop from 2 to square root of n. So if I have explicitly checked for 2 and 3 outside this loop, what will happen? I don't have to check for these numbers 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Because if the remaining number is not divisible by 2, then it cannot be divisible by any of these other numbers also. So I can simply strike out all the multiples of 2. Similarly, if I handle 3 explicitly, I don't have to check for these numbers 3, 6, 9, 12. 12 is already striked out, but still we can avoid these numbers, 21. So all these numbers don't have to be checked. The only numbers that we need to check are 5, 7, 11, 13, 17, 19. So numbers like these only have to be checked. So we need to begin with 5, then we need to check for 5 plus 2, then we need to go to 5 plus 6, 11, then we need to check for 11 plus 2, 13, then we need to go to 11 plus 6, 17, and then 17 plus 2, 19. So the same logic that we wrote for prime number can be used here to save iterations in this code as well. Now please pause this video and try to write down more efficient implementation. Here is implementation of the more efficient solution. We explicitly check for divisibility by 2. then we explicitly check for divisibility by 3, then we check for remaining numbers, and when we have already checked for 2 and 3, we strike out many numbers. You can notice that we increment I by 6, not by 1, and that saves many iterations. We do almost 1/3 iterations inside this loop. So this way, if we run it for n equal to 450, we'll first print 2, then we'll have n equal to 225, then we'll print 3 2 times, we'll go inside this loop 2 times, and then we'll have n equal to 25. And after we get n equal to 25, we'll come inside this loop and we'll begin with I equal to 5. So when we begin with I equal to 5, we'll go inside this loop 2 times and we'll print 5 2 times, right? So we'll get 5 2 times, and after that we'll notice that I plus 2 is not divisible by for the remaining n because n is now 1. So we'll come out of this loop and n is 1, so we'll not go inside this if condition also, and we'll not be printing n. See, this condition, if you notice, it's greater than 3 now, not greater than 1, because 2 and 3 prime factors are already handled. So if you have a remaining prime number, it must be greater than 3. It should be 5, 7 or anything. You will get a prime number at the end, right? And this happens in the case when your largest prime factor has only 1 power. In that case, you will come here, but that prime factor would be greater than 3 because 2 and 3 are explicitly handled here. Let us now talk about time complexity of this solution. This solution will go into the worst case when n is prime. When n is prime, you will not go inside this while loop, right? And you will not also go inside this while loop. So you will not drastically reduce n. So this outer loop will run theta of square root of n times, right? It's going to run theta of square root of n. We can say square root of n by 6, right? But these constants do not matter in asymptotic analysis. So we can say it's going to run theta of square root of n in case of prime numbers. We'll never execute the inner loop. See, if the number is not prime, then it's going to run less times, because when you go inside this while loop, right, what you do is you divide the number n and your n is reduced drastically, right? So for composite numbers, it's going to take less time. For prime numbers, you will never go inside the while loop and it will run all the iterations of this outer loop. And for prime numbers, you will have the time complexity as theta of square root of n.